In this lesson, we are going to look at multiplicity and sketching polynomials. So this is going to kind of summarize a little bit of what we did in the investigation previously, and it's going to help us or allow us to sketch different polynomials of different degrees. So it's going to tell us or give us some tips and some strategies on how to do that. But first, let's look at our different functions and look at some of the characteristics. So the first one we're going to deal with is a linear function, right? So for a linear function is one that we should be most common with, and that is basically a straight line. So when we look at a linear function, as we see here, the graph is a line. So in a linear function, the graph is a line. There can be up to one x-intercept. As we can see here, there's one here. Right, there can be up to one y-intercept, which would be here. But there may be some cases where there are none. Right? We could have a horizontal line, something like this. There's one y-intercept, but there's no x-intercept. And I could do the same thing with a vertical line. There'd be an x-intercept, but there is no y-intercept. So that's why we say there can be up to. And the final thing is that it crosses the x-axis as a line. And you might be like, well, what the heck do you mean by that? We'll come back to that later, but we see here it crosses the x-axis as a line. And we'll come back to that, but that's what we want to describe a linear function as. The next one that we look at is a quadratic function. So again, we should be familiar with quadratic functions. These are the two, linear and quadratic are the two main ones that we've dealt with before. So that should be what we are most familiar with. And a quadratic function would look something similar to this U shape. Maybe it's like that. Maybe it's like this. Maybe it's something like that, where it's just touching the x-axis at one point. These are examples of quadratic functions. Now, for a quadratic function, the graph is what we call a parabola. So the graph is a parabola. It can have up to two x-intercepts. Right? We see here, this example, there are two x-intercepts. We see here there is one, and we see here there are no x-intercepts. So it can have up to two maximum. There will be one y-intercept, right? Because of the nature of this quadratic function or the quadratic functions, because of these lines continuing upwards or downwards, they will eventually cross the y-axis at some point. Now, if we have two x-intercepts, the graph crosses like a line. So if we have two x-intercepts, the graph crosses like a line. We can see here it crosses like a line. If there is one x-intercept, the graph crosses like a parabola, which we see here. And what we mean by crosses like a parabola is that it touches the x-axis as either a maximum or a minimum. So another example could be it will come up, it touches our x-axis at one point, still considered an intercept, and then it comes back down and away. So that might be an example of the opposite version of what we see here. But that's what we mean by it crosses the x-axis like a parabola. The other characteristic of a quadratic function, we've seen it. We might not have always described it like this, but the ends of the graph enter and exit in the same direction. So what do we mean by that? Well, if we look at these two ends here, they're both going in the same direction. So this graph is going out here downwards and going here downwards, right? Or if we're coming in from the bottom, we reach our peak and we're exiting in the bottom as well. We're coming in from the top and we're coming out to the top as well. So that's what we mean by enters and the ends enter and exit in the same direction. So basically they're headed in the same direction, either both up or both down. So those are the two main types of functions that we've looked at, right, that we've talked about before. The next one is a cubic function. So a cubic function looks a little bit different. Right, so a cubic function looks something similar to this. This would be considered a cubic function. So a cubic function, it could also be drawn something, let me change this a little bit just to make it a little bit more compact. Could look something like this. Maybe it looks something like this. Maybe it just kisses and looks something like this. These are all examples of cubic functions. So in order for it to be a cubic function, it should look something like this. And remember, cubic would be something with x cubed. It must have between 1 and 3 x-intercepts. So if we look here, there's 2, here there's 3, and this one there's 1. So there must be between 1 and 3, right? In all the scenarios that we look at, there has to be between 1 and 3 x-intercepts. There's no case where it would not have any x-intercepts, or there's no case where it'd have more than 3. Another characteristic, the graph enters and exits in opposite directions. So the graph enters and exits in the opposite direction. Right, so if we look, this end is going down, this end is going up, down, up, down, up. Right, so they're moving in opposite directions. And it can cross the axis or x-axis with what we call S pattern. So our linear function crossed in a line. Our quadratic function could cross in a U or a parabola. Our cubic function could cross with an S pattern. So the very basic, or the most basic shape, or cubic function, would look something like that. So that's where it crosses the x-axis in what we call an S pattern. So that's the most basic form, the most basic version. Finally, a quartic function. So this would be one that is to the power of 4, or have a degree of 4. This could look something similar to something like this, kind of like a W. It could be the same idea, but up top. It could be flipped like this. Maybe it only touches once. Keep in mind the cubic function could be flipped as well. We'll talk a bit about that later. We'll look at some examples of that, possibly in some of the examples that we look at. But these are all examples of quartic functions. So this can have anywhere from 0 to 4 x-intercepts. Right? If we look at some of our examples, there's 1 x-intercept here. There's 1, 2, 3, 4 here. There's 1 and 2 here. And here there are 0 x-intercepts. Right, so in our quartic function, we can have anywhere from 0 to 4 x-intercepts. Another characteristic, the graph enters and exits in the same direction, which we've seen before. We've seen this before in quadratic functions. So we've seen this before. And if we were to look at the most basic quartic function, which would just be x to the power of 4, nothing else, no plus minus, nothing else, no x cubes added on or anything like that. A quartic function, degree 4, the most basic quartic function, you could say y equals x to the power of 4. It would look something, you can graph it and get a better example, but it would look something like this. That would be the most basic function, or most basic version of a quartic function. Now, if you were to look at that, could you tell me that that is not a quadratic if you're looking at it? And it would be hard just by looking at that graph for you to tell me that it wasn't a quadratic function based on what we see. If we see what the equation was, obviously you can tell the difference. One would be to the power of 4, one would be to the power of 2. But the idea is that in the most basic terms, this quartic function does not provide a new shape when crossing the x-axis, right? Because you couldn't tell me if that is quadratic or quartic. So it does not provide a new shape. Similar to how, well, not similar, but kind of the opposite of a cubic function. We said this was the most basic, y equals x cubed. That this creates a new shape as we come across the x-axis. This is kind of S pattern, right? It's changing, this kind of like comes from the bottom up and shifts over. So what we mean by this to the power of 4, this quartic function, there is not a new shape, because if we can see in the most basic shape, it would cross as a parabola. Right? Even in all these other examples we see here, it's crossing as a parabola, crossing as a line, right? It's just a line crossing as a parabola. Right? So there's no new shape in this quartic function. So it does not provide a new shape or a new kind of way of crossing the x-axis. So this brings us to what we call multiplicity. And multiplicity basically is a concept that relates the root of a function with the degree of the factor or root. Right? So when we break down a polynomial, we break it down into different factors, and it relates the root of the function, right? So each factor with the degree. So depending on what the degree is, that will determine kind of what the nature of that factor is. And we could be given polynomials, and again, sorry, that might be a little bit hard or confusing of a definition, but we'll look at some examples, so hopefully kind of get a better understanding of what we mean. Now, we could have two forms of our polynomials. The factored form, right? So f at x equals a coefficient times x minus m to the power of n times x minus n to the power of p, and so on and so on and so on. Or we could have it in the general form, ax to the power of n plus bx to the power of n minus 1 plus cx to the power of n minus 2, and so on. And we've dealt with both forms, right? We've dealt with general forms, and we've turned it into factored forms. But when we're dealing with polynomials, polynomials, so these would be generally different from our quadratics and our linear functions, right? So higher degrees or cubic or quartic functions. The general form is not easy to graph. Even if we're looking at a quadratic, it's still not easy to graph, right? And I'll put it specifically by hand, right? Polynomials are not easy to graph by hand if we're given the general form, right? The factored form is a lot easier because we see these different roots. So we're going to be focusing on the factored form. So when we graph or sketch these polynomials, you'd be given the factored form. Now, in general, we're going to look at what we see or what occurs with these different degrees because it's going to help us sketch it. So if we look, we're going to start looking at degree 1 and work our way down to degree 5, and hopefully we kind of see a pattern as we go through. So degree 1, right, linear function, for an example, x minus 2 raised to the power of 1. Normally we wouldn't see that. So if we don't see an exponent, we assume it's 1 or a degree 1. In this case, if this was a factor, the x-intercept would be 2, right? We set this equal to 2 or equal to 0, move the 2 over. This is x equals 2. So the only way it equals 0 is if it is if x equals 2. So characteristic, what does it look like? Well, at this value of 2 on the x-axis, we're only looking at the x-axis, a function or a polynomial or a factor with degree 1 would cross as a line. So just cross as a line, right? Either going up this way or it might be coming down, right? All it's saying is it's just going to cross as a line, your x-axis. If it's a factor or a root that has degree 2, and you might hear me saying root, remember when we looked at quadratics, the factors are considered the roots, which are considered the x-intercepts, which are also considered the solutions. So every time we've been solving, we've essentially been finding the x-intercepts. So getting back to this, degree 2, so again looking for that exponent 2, the x-intercept would be 2, because if we were to set this equal to 0, move the negative 2 over, it becomes positive. If we're dealing with a degree 2, the characteristic, and we mentioned this in the summary, it touches or crosses the x-axis as a parabola. So something like that, where it just touches at one point, the vertex. Now, it could be flipped. It could be the other way. It could be coming up from the bottom as well, like that. That's also fine. Right, so either or works. Maybe we'll just keep it off this one. We'll say or something like that. So either way would work. A cubic function, same idea, cubic function, we talked about in the summary, it crosses in an S pattern. So something like this. Actually, I'll stretch it out a bit. Just try to keep it consistent. There we go. So it crosses in this S pattern at the x-intercept. So if it's a cubic function, it's going to cross like an S at the x-intercept. If we look at the quartic, or the fourth degree, degree 4, we said in our summary, it crosses like a quadratic. We've seen that before. We've seen that actually up here in degree 2. So we've seen this one before. This is a repeat. And if I look at the next one, what do we think x to the power of 5 would be? Well, if x to the power of 4 or degree 4 was a repeat of the degree squared, to the power of 5 or degree 5, if you guessed that it was a repeat of the cubic function, you would be right. So this, we're repeating the shape. So it's a repeat at the x-axis. So what we see is that after degree 3, we start to repeat the shape that it crosses the x-axis in. So realistically, we only really need to focus on or know or memorize, you could say, these 3 different shapes. Degree 1 crossing like a line, degree 2 crossing like a parabola, and degree 3 crossing in an S shape. The reason we only need to know those 3 different shapes is because it starts to repeat. So when we have an even degree, so degree 6, 8, 10, we are going to see this parabola shape. If we have an odd number after 3, we're going to have this S shape. And we can conclude then that the functions with odd degrees, exit or enter, exit, in opposite directions, and if they're even degrees, they exit in the same direction. So this implies the idea of the parabola shape or the S shape when dealing with how does it touch the graph or the x-axis. So let's use this idea to help us sketch our graph by hand, or sketch these polynomials. So let's sketch these following function, right? So we have our polynomial function f of x equals 0.5 x plus 4 squared times x plus 1 cubed times x minus 2 times x minus 4 to the power of 4. So first we want to figure out our degree. Well, the degree is, when we're dealing with a factored form, we talked about this in the investigation, is add up the exponents on your factors. So in this case, degree 2 plus 3 plus 1 plus 4. Sorry, not 4. That's a 4. That should be a 2. My mistake. Let's just change that to 2. This gives us a degree of 8. So because it is a positive degree of 8, we can say it exits and enters in the same direction. We can also say that because the a value, or the leading coefficient, a equals 0.5, here we could say it opens up. Negative would be opens down. So that means that it should be opening upwards, something like that. Next thing we want to do when we're sketching this is think about what are the roots, what are the solutions. So in this case, I'm going to look at each factor, each term that has an x with it. I'm going to look at each factor. So in the first one, we'll color code this actually. So in the first one, x plus 4, that gives me a root or a solution. Sorry, let me say roots. X is equal to, the first one, x plus 4, that gives me a solution of negative 4. The next one, x plus 1, that gives me a solution of negative 1. Next, I have x minus 2, that gives me a solution of positive 2. Just change the size of this. And the last one, x minus 4, gives me a solution of positive 4. So those are my 4 different solutions, or my 4 different roots, or my 4 different x-intercepts. So what I'm going to do is I'm going to put a point. I'm going to start with each one, sorry. Let's start with the first part, negative 4. I'm going to put a point there. Now, if I look at that factor has a degree of 2. So that means that this point, or this function, has to touch that factor as a parabola, or this root as a parabola. And the reason it's looking like this is because in order, it's a positive degree, so it enters and exits in the same direction, and it opens up. So this would be it opening up. I'm going to draw an arrow on the one side. I'm not going to draw the arrow on the other side, and we'll talk about why. Because we haven't finished the graph. There's more to it. I'm going to look at the next solution, negative 1. I'm going to put a point there. This has a function of, or a degree of negative, or of 3. So this means that it has to touch or cross the line in an S shape. And normally we said our S shape was something like this. However, if I look at the graph, that doesn't make sense, because then how is this going to come back down and connect up? Right? If I look at where this graph ended, it ended up top. So that means somehow my graph, or this x-intercept, the function needs to cross in this kind of manner. I'm I'm going to move over to my next solution, 2. Put a mark there, or point there. There's an x-intercept there. It has a degree of 1. So that means it's going to cross in a line. Why am I drawing the line this way instead of this way? Well, because there's no indication that it's crossed before, so the line has to come from the bottom and then crosses the x-axis here. If there was another x-intercept somewhere around here, then yes, I would put it downwards, but because based on what I've already know from my function, it has to somehow come up from underneath, from the negative values into the positive. The last one at positive 4, because it has a degree of 2, it needs to touch as a parabola. So I'm going to draw it something like this. Again, the reason it's like this and not something like this where it opens down is because there's no way for this line to come back down and around without crossing the x-intercept or the x-axis, but nothing has indicated to us that it crosses anywhere else. And we see by the factors or the roots that these are the only 4 spots where it crosses the x-axis. So I'm going to draw it something like this. And at the end, the last one, I can extend it further because this is telling me that it continues on, right? There's no other x-intercept, so this is going to continue on upwards. And that does help, that does match with something we've already found. We said it enters and exits in the same direction. Well, once these are all connected, here's where it enters, here's where it exits. It's both in the same direction. It is also both opening up, which matches the characteristics that we've seen so far. Next thing we're going to do is just connect our functions or connect our values. So I'm going to roughly do it, right? We're just sketching it in this case. So we're just sketching it. So it doesn't have to be perfect. We're just getting the general idea of what this shape is, or what this function is going to look like. So it's going to look something like this. Is it going to be perfect? No, right? We're just sketching it to see what does it look like. And this is what it might look like, based off of what we know about each root and the degree of each root. So we've looked at an example of how to draw or sketch our function or polynomial. Now what we're going to do is go look in the other direction or the other kind of method and think about how can we determine the equation of a polynomial. So we're going to kind of reverse our thinking from the last one, right? We're going to identify the roots first. So I'm going to go through and look for where does it touch the x-axis. Well, I have a value here and a value here. So I have 2 values. So right now what I can say is for my function, say y equals, you could say f at x if you don't want y. So y equals, I know I have a solution of x plus 4 because that would give me this intercept. And I know I have one of x minus 2, which would be this intercept. So I know I have that much so far. What I'm going to do next is think about what is the degree of each root. And in order to find the degree of each root, this is where we need to understand how does our graph or how does our function cross at each root. So if I look here, it crosses as a line. So the only one that crosses as a line would have a degree of 1. If I look at my second solution, this crosses as a parabola. So that means it has to have, or it should have, a degree of 2. We wouldn't really indicate that it has a higher degree than that, because realistically, if it has a degree higher than 2, chances are it could be factored to as a degree of 4. Or sorry, if it was higher, if like another value like a degree of 2, 4 or 6, it could probably be rewritten or factored as a smaller degree. So really, like I said, we're only really focusing on degrees 1, 2, and 3 for the most part, especially if we're coming up with the equation. If we're not given the equation, we are given and we are graphing the equation, then it would be different. But in terms of coming up with our equation, we'll keep it as either degree 1, 2, or 3. So that's what we know right now. Now, there may be a coefficient, a value in front, an a value. So technically, I'm going to erase this part. I'd have y equals a times x plus 4 to the power of 1 times x minus 2 to the power of 2. What we need to do now is figure out another known point on the graph that is not an x-intercept. So it might be an exact value, or do your best maybe to approximate. Here we can see we have one. This is 4 and 5. Actually, let me use a different color to make it stand out, or a little bit darker. 4, 5. So I'm going to use that point, plug it into my equation, and solve for a. So in my equation, I'm going to rewrite it. Y equals a, x plus 4. I don't need to put to the power of 1, x minus 2 squared. I'm going to plug in these coordinates, 4, 5. So 5 is my y value. A I don't know. X is 4. So 4 plus 4. And then 4 minus 2 squared. Now I'm going to go through and solve for a. So 4 plus 4 is 8. 4 minus 2 is 2, and then that squared. 5 equals a times 8 times 4. 5 equals a times 32. Divide both sides by 32. I get 5 over 32 is a. So this tells me then what my coefficient is. So therefore, the equation for this function would be y equals, or f at x equals 5 over 32 x plus, x plus 4 x minus 2 squared. So that would be the function, or the equation for this polynomial function. So again, similar to what we were doing in terms of sketching it, we're looking at each root. The only difference here is if we have to determine the a value. So let's look at 2 more examples. X plus 5 to the power of 5, x times x to the power of 4, times x minus 2 to the power of 1. So first things first, like we said, we need to figure out the degree, because that's going to tell us how does it enter and exit overall. So we add up our exponents on these factors. 5 plus 4 plus 1 equals 10, which is even, so it opens and exits, or sorry, enters and exits, I guess that's the term we've been using. Enter and exit the same direction. If we look at the coefficient, in this case, our coefficient is positive. We could say it's 1, so that means it opens up. So we know some general characteristics about how it's supposed to look. Finally, we now look at our roots, or our solutions. Tell us where our kind of key points are. So x is going to equal, we have, if I look at the first one, plus 5, so x equals minus 5. So the first solution. The next one is just x, or 0. Right, because what I'm doing to figure out these solutions, I'm setting each factor equal to 0. And then lastly, x minus 2 or plus 2 would be the other solution. So those are our 3 roots. Now I'm going to draw each one. So negative 5, 0, and 2. And I'm going to go back and look at how does each how does each factor cross the x-axis? And that's where I'm going to look at the degree of each factor. So if I look at x plus 5, it's to the power of 5. So that means it needs to, it's an odd factor. It's not 1, so it's, or sorry, an odd degree. So not 1, so it's going to cross in the S shape. So our options are either something like that or something like that. In this case, because it opens up, we know that from the initial or from the coefficient, it means it should come across something like this. Is how it should start. If I look at x to the power of 4, my next value, that is a positive, or an even degree, an even degree. So that means it has to touch as a parabola. Something in this form. The reason it's like this, where it's opening down instead of like this, is because there's no indication of anywhere for this line to come back and cross the x-axis. We would see another solution somewhere showing that it crosses as a line, which we don't. So it has to be something like this. And then lastly, for the last one, because it's a degree 1, that means it's crossing as a straight line, which does make sense because it does need to open up and it enters and exits in the same direction. So based on the main characteristics that we looked at initially, this does make sense. Now that I know the characteristics at each root or solution, I'm just going to connect our roots. So our graph should look something like this, right? Or if we were to sketch it, look something similar to this. Finally, we want to determine the equation for this polynomial. So again, we need to first, so we just did an example of this, we need to determine the equation at each, or we need to look at each root. So the first one, we see where it crosses the x-axis there, here. We don't need to worry about the y, we know it's coming down and somewhere it comes back up, and it touches here. So next, so I'm going to write that out. So I'm going to use the different notation. F of x equals coefficient. My first one, since it's minus 4, it'd be x plus 4. Second one, x plus 2, because it's negative 2, right? It's opposite. And finally, x minus 3. So those are our 3 solutions. We need to look at the degree of each, though. So if I look at the first one here, this crosses in that S shape, right? It's coming up and then it switches directions. So that's that kind of characteristic of an S shape. So that means a degree of 3. If I look here, it's crossing as a line, right? It's just a one line crossing. So that means an exponent of 1. And if we look here, this is crossing or touching the x-axis as a parabola. So that means a degree of 2. This is our function right now, and we don't know what the coefficient is. So the next step was to find a nice point. So nice point, right, looking might be here, -1, -3. So I'm going to plug those two values into our function. The -3 replaces the f of x, so -3 equals a, which we don't know, -1 for x plus 4 times -1 plus 2 times -1 minus 3 squared. I'm going to go through and solve. So -3 equals a times 3 cubed times 1 times -4 squared. 3 equals a times 27 times 1 times 16. Negative 3 equals a times 432. To get a by itself, I'm going to move the 432 over. I get negative 3 divided by 432, which is a. So then therefore, f at x is equal to negative 3 over 432, x plus 4 cubed, x plus 2, the power of 1, x minus 3 squared. So that is the equation for this polynomial. And we can look at some of the characteristics and go back, right? The main characteristic for our polynomial, right? It's a negative coefficient, so that means it should be opening down, which we do see here, right? It opens down. That's not to say we can't have some parts that are going up, but overall it's opening down. If we look at the degree, 3 plus 1 plus 2, 3 plus 1 plus 2 is 6. That's an even degree. So it should be entering and exiting in the same way, which we do see on the two ends. They're both in the same direction, right? And we know about the characteristics of our, or of each function, or sorry, each solution or each root, because that is how we were able to determine the degree of each factor or each root. So a lot to kind of really digest because it is a lot of new information. The main thing that I would suggest really focusing on, if you need to remember something, is remembering the characteristics of each of the first 3 degrees, 1, 2, and 3, and then recognizing that it starts to repeat. So then 4, 6, 8, 12, so on, would have the same kind of characteristics as a quadratic or degree 2. The odd numbers after 3, so 5, 7, 9, 11, would have the same characteristics as a degree 3 or that S shape. The other thing is recognizing odd degrees enter and exit in opposite directions, even enter and exit in the same direction. Right, so those are the main characteristics that we really need to focus on, because that will help us, 1, sketch our functions, and 2, determine the equation of our functions. Right, so lots of practice on this. So make sure you are practicing, because this is definitely something that was not taught previously in grades 10 or 11, unless maybe you took, actually not even in the 11 university stream. So make sure you are practicing, make sure you are asking questions, make sure you have your notes for when you're going through and either determining the equation of a polynomial or sketching a polynomial.